I'm going to break this last topic into two videos so you can kind of skip past this first part if you decide you don't care as much as what I'll tell you. I want to give you a sense for where we can get error bounds for these approximations that we're making with polynomials, only because it connects to a couple of things that we've already done. It's something that you may have seen in Calculus 1. The explanation is not super important for how to actually do the problem. So I'll give the general explanation, I'll show one example, and then in a separate video I'll do the two other examples. What we're trying to do is see how much error we would get by using a Taylor polynomial approximation to a function. And to kind of understand this, keep in mind that what we're really trying to do here is think about how we can build our function, our original function, not as just a Taylor polynomial of degree n, but rather as an infinite polynomial. So those things that we were working on at the very beginning of this unit were infinite polynomials, and so they would look like the Taylor polynomial yeah, I'm running out of room already. But they would just keep going. So you'd have the next term, and so on. So they would go on forever. So that would be the infinite polynomial. It would just keep going and going and going. In the terminology that we use for series, we would have called this part, we would have named that S sub n, and all that stuff that's at the end, all the infinite stuff at the end, we would have called that R sub n. So we now have a different way of referring to S sub n, where what we're calling P sub n for polynomial is really just the S sub n from what we did before. So the nth degree polynomial is the thing that we're plugging into to get the sum of the partial sum up to n. And then Rn is everything else. So what's interesting is the theory tells us that the Rn part here, actually it is an infinite sum, but there's a theorem that tells us that the Rn part, that whole infinite sum, is actually equal to just this part, nothing else, just that next term, with the key difference being that here I'm not evaluating at A. You see I have the letter C there, and the theorem says this has to be true for some value of C between X and A. So in other words, between the center of the approximation and the X that you're plugging into it. So for each X that you would want to use to evaluate this, there's going to be some C that makes this exactly the remainder. There's no practical way to know what the value of C is here. And so this doesn't really help us in practice very much, but what it does do is it allows us to have to come up with a really easy upper bound on the error. Remember, the entire remainder, that entire infinite sum, is the real error, and so this value, in absolute value, that's the real error that I would get trying to use the polynomial at x for an approximation of the function at x. What we can do is say, well, that's less than or equal to m times n factorial x minus a to the n plus 1, where I'm using the letter m here to represent m is the largest. I still have absolute values there. M is the largest that the absolute value of that next derivative gets. So the idea here is we don't really know what the C is inside of this, but what we can do is we can look at a graph of this function, the n plus first derivative. C has to be somewhere between x and a, and we can just ask ourselves, what is the biggest this ever gets for values of C between x and a? So we don't know what this is exactly, but we will be able to very quickly and easily figure out the biggest this could be. And so if we know the biggest this can be, then we know the biggest this can be, and that's the upper bound on our error. The proof that something like that works uses what you may have seen in Calculus 1. It's called the mean value theorem, and it's not very difficult to show that this result is true if you know the mean value theorem. I'm not going to go into it here, but if you're interested, look up online where the remainder theorem comes from for Taylor polynomials, and you'll see that it's just an application of the mean value theorem, and it's actually kind of a clever application of it. It doesn't require any kind of higher calculus, but it just requires thinking about how you would get this problem from the information that we have so far. Anyway, perfectly doable. And if we had class, we would go into it a little bit, but I'm going to leave it at that for now. So in practice, the way we can use this theorem looks like this. So here is the work that we did on the day 2 worksheet, where we found an approximation for the square root of 18 using a cubic polynomial. And if you remember, that cubic polynomial was centered at 16. That's what we did last time. So we built a cubic polynomial centered at 16. To do that, I started with the square root function. I took the first derivative, second derivative, third derivative. I evaluated each of those derivatives at 16. So I plugged 16 into each of those, and that gave me these numbers, and those became the coefficients in the polynomial. What I've done on the screen here is I've made a space for the fourth derivative, because the fourth derivative is going to give us information about the error bound. If I'm using the cubic polynomial, if I'm using 3 for n here, then that means the m that I'm looking for is going to be a bound on the fourth derivative. So if I use 3 derivatives to build my polynomial, I need the fourth derivative to understand the error. So in practice, that means I need to calculate one more derivative here. So negative 15/16 x to the negative 7/2 will be my next derivative. I put some x's here just to discourage you from just immediately plugging 16 in. That's not what we're doing here. So I have negative 15/16 x to the minus 7/2. And you see I've plotted it here. And remember, the center of my approximation is at 16. So that's the middle of the approximation. So I want to make sure I plot it in a way where that looks like it's in the middle of my screen. So this is a graph of negative 15/16 x to the minus 7/2. The capital M that I need is supposed to be the largest that you see on the screen, the absolute value of this function for values of x between 16, the center, and 18, the number that I'm plugging in. So I only care about this part of the picture. Only care about the values between 16 and 18 that I'd be putting in. And I want to know what's the largest absolute value of this curve I ever see. Well, the absolute value, one way of thinking about absolute value is that it is just the distance the number is from 0. So when I'm looking for the largest the absolute value gets, what I'm looking for is what is the furthest this curve is away from 0. And you can see that happens over here. Right over on this side, the curve is the furthest away it ever gets from 0. I don't care at all that there are negative numbers in there. I want to know how far away it gets. I want to know what is the largest the absolute value is for this thing. So I can see from my graph that it's somewhere around negative 0.0006, but I can see that it's actually just right above 16. And so, in fact, I could just plug 16 into my fourth derivative function, and it would give me the exact answer. The only reason that's tempting is because these do come out to be nice. They do come out to be fractions when I plug in a number like 16. I can actually get that exact value. But we can just read the graph. We'll see on the flip side that sometimes just reading the graph is good enough. So if you were just reading the graph and you couldn't really tell, exactly where this is, you might just use this value, because that is bigger So I feel 100% sure that this is true, that the largest well, I shouldn't say m's less than or equal to. Oops. So I'm trying to figure out what I could use for m. So using m equals 0.00008 would be totally fine. I can see that every y coordinate in the green box that I drew has absolute value less than that. But if you want to be more precise, you can actually figure out exactly what the y coordinate is there. I did do that because it was an easy number to plug in, and so I got so the exact value I got was 15 over, good Lord, 262,144. So that's a pretty awful looking number. But that is about 0.00057. So it turns out that that dot really is a little bit less than 0.006. I could have used that. But it doesn't really matter what value of m you use. You want it to be the right order of magnitude, and you want to make sure that m is greater than or equal to the absolute value of the derivative. But you can just get it from reading the graph. You don't have to be very precise about it. So the theorem says that the error would be written this way. So f of 18, that would be the square root of 18, minus the approximation at 18. So that's the actual error. So remember, we call that absolute error on the last slide. The theorem says that's no more than m, I'll just use 0.006. I'll scroll back up so we can see, oh, the m is there. M times 18 minus 16 to the fourth over 4 factorial. So it has exactly the same form as the coefficients of our of the polynomial, but just at the next value of n. So I have so 18 minus 16 to the fourth over 4 factorial. That's what I wrote down there. Anyway, and so this will give you roughly what they'll give you an absolute value, give you an upper bound on the absolute error for your estimate. And that's about 0.00004. Don't forget that we did calculate the absolute error on the day 2 worksheet. And we found the real absolute error was 0.00003. Oh no, it wasn't. 35. That's what we came up with when we saw what the real absolute error was. And so we can see that that's saying that it's at most 0.0004 is actually pretty close to being right. And but knowing that that's how close we are as possible without actually calculating the real value of the square root of 18. So we will see there are cases where we have no option. We can't calculate the exact value of our function. And so this error bound will be the only thing that we have to tell us how close we are. And so it's good to see it in a few cases where we can tell that the error bound really is pretty close to being right. So at this point, you should look at the document 2, the second document that's posted. It has 2 examples of additional problems to do this with. Give them a try, see what you think about the error bounds, and then watch the next video where I'll walk through those.